Okay, so today we will discuss about the helium-neon laser. Helium-neon laser. So in that the helium-neon laser, this also gas laser only, gas laser, but it is continuous laser. So it is a, so previously we discussed about the ruby laser, that is discontinuous laser. Okay, so now we are discussing about the helium-neon laser. So this is a gas laser and it is continuous laser. Continuous laser. Okay, so first of all, the helium neon laser consists of three essential components. That means every laser consists of these essential components. So first one is pumping source. So here what is the pumping source we are using? So high voltage power supply. High voltage power supply. Okay, so and gain medium. So laser glass tube or discharge glass tube we will use as a gain medium. So gain medium is different, active medium is different. Okay, so active medium means so which is the component it's participate in a lasing action. Okay, here gain medium is so discharge glass tube. Okay, so active medium, active medium is neon. Active medium is here neon. Okay, and resonating cavity we know that so this is two parallel mirror plates will used as a resonating cavity. Okay, now construction of helium neon laser. Helium neon laser consists of a gas discharge tube of length 80 centimeter and diameter of 1 centimeter. See here, so this is the gas discharge tube. So this length is 80 centimeters and just diameter is 1 centimeter. Okay, so remember that ruby rod length is just 4 centimeters here. So this is 80 centimeter. Okay, and the tube made up of quartz and is filled with mixture of neon under of 0.1 mm of Hg and helium under the pressure of 1 mm of Hg. Okay, here so inside this tube, so this is the quartz made with quartz tube. So this tube contains helium and neon gases. Helium and for neon gas is 0.1 mm of Hg. So for helium, it is 1 mm of Hg. Okay. So what is the units of pressure? So it will be either Pascal or mm of Hg. Mm of Hg means if you will take normal normal at STP, what is the pressure? Okay, STP, what is the pressure means 76 normal pressure in atmosphere. At STP conditions. So that is the normal pressure at atmosphere is 760 mm of Hg. Okay, if you will take on that tube, so that pressure should be very less, very less. That is just so 0.1 mm of Hg. Okay, so for in neon gas, so 1 mm of Hg in helium gas. Okay, so in the quartz tube, we are taking helium neon mixture. About ratio is very important. 10:1. 10:1. So neon gas is 10 times greater than the helium gas is 10 times greater than the neon gas. So helium neon is 10:1. Okay, so 10:1. This ratio you have to remember, and pressure, how much pressure. So we are applying that also important. Okay, so on that neon gas just 0.1 mm of Hg pressure, and in case of helium gas, so that is 1 mm of Hg, and the ratio is 10:1. Helium, so that means helium is 10 times greater than the neon. So helium neon ratio is 10:1. Okay, hence the number of helium atoms are greater than the neon atoms. Okay, the mixture is between a set of parallel mirrors forming a resonating cavity. See here. So this total quartz tube placed inside the mirror resonating cavity. Resonating cavity is nothing but two parallel mirror plates. So here one mirror plate, here another mirror plate. Okay. So one of the mirror plate is completely reflecting. That means it is fully silver coated. It is fully silver coated this side. Okay. So this side it is completely. See here. So if you will take this side, so it is completely silver coated. So completely silver coated. That's why what happened, whatever light is instant on this plate, it will be so fully reflected back, completely reflecting back. Okay, there is no transmission of light instant on the mirror. Similarly, this is partially reflected, partially reflected. That means it's also partially silver coated, partially silver coated. That's why it's reflecting approximately so 95% reflecting back, only just 5% transmitted. Okay, so this is the construction of helium neon laser. So helium neon laser. So first of all, we are taking so quartz tube. Quartz tube. In that quartz tube, we are filled with helium neon gas, just 10:1 ratio. 10:1 ratio, and pressure on helium neon gas is so on helium it is 0.1 mm of Hg. So on neon it is 0.1 mm of Hg. Helium 1 mm of Hg. So those points you have to remember. And one more thing. So this total equipment is so placed in the resonating cavity. So resonating cavity means so two parallel mirror plates. One mirror plate is so fully reflected. Another mirror plate is partially reflected. This is about the construction of helium neon gas laser. Okay, now working. So what is the working of the helium neon gas? So how it will be works? So when an electric discharge is placed through the gas mixture, the electrons are excited down the tube. See here. So here this is the tube here. So one end is connected battery, one end is connected to the cathode, another end is connected to the anode. Okay, so now we are giving some power supply. If you give power supply, what happened here? So electric discharge will be takes place. Electric discharge will be takes place. So because of that electric discharge, so high electric field. So because of that high electric field, what happened inside this tube? Inside this tube, so electron will flow from one direction to another direction with a very high velocity. With very high velocity. So 1 minute, Amma. Yeah. So now I am continuing. So this total quartz tube is placed inside the high electric field. Okay. So this gas. So because of this, what happened? So if you placed in electric field, so electric discharge will be takes place. Electric discharge will be takes place. So that in that there are so many electrons will be there in helium and neon. So those electrons will move from so one side to another side. That means those electrons are accelerated. Those electrons are accelerated. Accelerated electrons are collide with helium atoms. Accelerated electrons are collide with helium atoms. So if the electrons are collide with helium atoms, means what happened? Those helium atoms will goes to the excited state. Okay, so that means whenever very okay, so these so one more thing, మీకు ఫార్వర్డ్ చేశారంట కదా 4500
టోటల్ ఇంటియాలి కదా 18500.
Okay, so now whenever we will apply the electric discharge here, so electron will move very fastly. So that means electrons are accelerated. These accelerated electrons so collide with the helium atoms. That's why these helium atoms will goes to the higher energy levels. See here. So because of the acceleration of the electrons, that ground state helium atoms will goes to the excited state. So those energy levels are here given. So 21s and 23s. So these are the energy levels. These are the spin energy levels. Okay, spin energy levels. So that means there are three types of energy levels will be there: electronic energy levels, so rotational energy levels, and vibrational energy levels. So electronic, so vibrational and rotational energy levels. Three energy levels will be there. How it will be, I will explain you. Okay, so now if you will take any atom, so any atom, there are electronic levels will be there. So if electron jump from so one energy state to another energy state, that is the electronic energy. That means n equal to 1 to n is equal to. So that is the primary quantum numbers we said now. So n equal to 1, 2, 3, 4. That those are primary quantum numbers. So we'll give the primary quantum numbers to electronic levels. Okay, and so next one is the so vibrational quantum numbers. So vibrational, after that rotational quantum numbers. So vibrational means so here sp, these are there, sp configuration. So for s, l equal to 0. So for p, l equal to 1. Okay, so these are the so vibrational levels. Another one is the rotational means based on the spin. So either it will be +1 or -1. Based on the spin, there is a some energy levels will be there. So those are the spin quantum numbers. So based on the spin also, there is a some rotational energy levels will be there. Okay, here, so if you will take only this number gives, so this 2 gives the, so 2 numbers gives the energy level electronic energy level. So that electronic energy level again separated into vibrational energy level. So that vibrational energy level again separated into spin energy levels. I think in spectral, so in chemistry, you know regarding about this all. Okay, so similarly here, so this helium atom will goes to the, so these excited states, these are the spin energy levels. So that is the, so second electronic level, and so this is a 1s is spin, first one spin state, another, so this is the plus off state, this is the minus off state. Okay, so like that, so this spin energy levels also divided like this. Okay, now so these are the so energy levels of the helium atom. So these also having metastable states. So metastable energy levels. These also metastable energy levels. Here also helium atoms will stay much more time. Here also, and helium atoms stay will much more time, and these helium atoms will react with the neon atoms. So these helium atoms, whatever the excited helium atoms will there na, so those helium atoms interact, that means again collide with the neon atoms. So yeah, sufficient long time, and collide with the neon atoms in the ground level. Okay, so these excited helium atom so collide with the so ground state neon atom. That's why what happened, those ground state neon atoms comes to the so equivalent energy states. So this is 2s, this 2s1 energy state of helium atom is equal to the 3s energy state of neon atom. Similarly, so this energy state is equal to the 2s energy level of neon atom. So that's why, so because of the collision between the helium atom and neon atoms will goes to the excited state. So those excited states are 3s and 2s. Okay, so these are the excited states of neon atom. So if you will take neon atom energy levels, so this is the 3p energy state, and this is 2p energy state. Okay, now so this is the 1s energy state. So here ground energy state will be there, okay. So now what happened here, so first process is, so because of the so electrons are, so we are applying here electrical discharge. Because of that electrical discharge, what happened, electron will move very fastly. So electrons are accelerated. These accelerated electrons are collide with helium atoms. So ground state helium atoms. So that's why those helium atoms will goes to the excited state. Excited state. So these excited state will also act as a metastable state. So those helium atoms will stay more time here. So those excited helium atoms again collide with the neon atoms. Again collide with the neon atoms. So because of that collision, what happened? Neon atoms will goes to the excited states. So neon atoms will goes to the excited state. So those excited states are so 3s and 2s, 3s and 2s. So these are the neon atoms excited states. Okay. Now so transitions. So transition will be takes place from so these excited states. Those transitions are 3s to 3p, 3s to 3p, or so 2s to 2p. Okay, or 3s to 2p. So based on the there are some selection rules will be there. So those selection rules are delta n equal to so plus or minus 1. So delta n means so that is the principal quantum number. Delta n equal to so 0 plus or 0 comma 0 comma 1 only. Okay, 0 comma 1. So delta n equal to 0 comma 1. And delta L. Delta L means azimuthal quantum number. Delta L equal plus or minus 1. Plus or minus 1. So those selection rules will follow here. If those selection rules are satisfied, then only lasing action is takes place. Then only lasing action is takes place. So here transition occur between the so 3s to 3p because here delta n equals 0. So that's why so selection rule is satisfied. So that's why here transition occur in between 3s to 3p. Okay. Again, so here also so transition will be takes place 3s to 1 is equal to so plus or minus 1. Delta L equal plus or minus 1. So that's why here also selection rule is satisfied. That's why so transition will be takes place. Lasing action is takes place in between 3s to 2p. 3s to 2p. Similarly, so here 2s to 2p also lasing action will be takes place. Lasing action will be takes place. Yeah, so how many lasers are emitted here? So three lasers are emitted. One is 3.39 micrometer, another one is 632.8 nanometer. So another one is 1.15 micrometer. So three lasers are emitted here. But so if you want only one laser, if you want only one laser means what we have to do? So we have to do with so we have to absorb the remaining lasers. So suppose only we want this laser, only we want this laser means so we'll so for absorbing these lasers so we'll use some filters, we'll use some filters to absorb the remaining lasers. Okay, so whatever we want here, so whatever so suppose if you want this laser so 3.39 micrometer so wavelength laser means we will use filter to absorb these two lasers. Suppose if you want so only this laser means so we will use a filter to absorb these two lasers. Okay, so like that. So generally so this is the major laser here. This is the major laser 632.8 nanometer laser transition. Okay, remaining also lasing action will be takes place. So but so that lasing action is very less, so very less transition will be there, very less intensity of the laser will be emitted. So because of these two transition, because of these two transition, very small amount of so very small intensity of laser will be emitted. Okay, so in this case multiple wavelength of laser will be emitted, multiple wavelength of laser will be emitted. Suppose if you want only one wavelength means we can use some techniques to reduce the remaining lasers. Okay, now so after that so here 2p to 1s, so there is a so emission will be takes place, that is the spontaneous emission, not stimulated emission. Okay, 2p to 1s, so there is a fast decay will be there. That fast decay is nothing but so that is a spontaneous emission, because so the 2p level is a not metastable state, not a metastable state. So similarly 3p level also not metastable state. Okay, so that's why so 3p to so 1s, 3p to 1s here So transition will be, so here 3p to 2p does not takes place, transition does not takes place because delta L equal to 0, so that is not a selection rule. Okay, so delta L should be plus or minus 1. Okay, so in this case delta L equal to only so 0, so that is del selection rule is not satisfied here, so that's why here so transition occur between 3p to 1s, 3p to 1s and 2p to 1s also, 2p to 1s also. Okay, so 3p and 2p are the not metastable states. That's why here spontaneous emission, fast decay will occur. Fast decay will occur. And here from 1s to so ground state. So here energy gap between 1s to ground state is very small. 1s to ground state is very small. Yes. So here 1s to ground state is very small. That's why so due to the collisions with the discharge tube here, so decay will occurs. So decay will occurs. So that's why there is no radiation will emit from this transition. So what we have to remember mainly here, so whenever electrons will collide with the helium atom will goes to the excited state. Okay, so that excited helium atoms again react with the, again collide with the neon atoms. Now neon atoms will goes to the excited state. Okay, so these excited state neon atoms are so comes to the different energy states. So those energy states are 3s to 3p and 2s to 2p. So based on the selection rule, again 3s to 3p. So these three are the lasing process. So lasers will occur. So because of these three transitions. Okay. Now so remaining transitions are the not a laser transitions, because so these three level are the metastable states. So that's why so here 3p to 1s also transition will be takes place, that is a spontaneous emission. So here 2p to 1s also transition will be takes place, that is also spontaneous emission. So that's why laser does not emit so from these transition. Okay, so this is a just fast decay. After that, so because of the collision, those neon atoms comes to the ground state. Okay, so again these neon atoms collide with these helium atoms. Again these neon atoms will goes to the excited state. This process is reversible process. This process is reversible process. That's why what happened here. So laser will be emitted continuously. Laser will be emitted continuously. This is about the helium neon laser. This is about the helium neon laser. Now applications of the helium neon laser. Okay, so there are this is a very less energy laser. So helium neon laser is very less energy laser compared to ruby laser. So this energy is very less. That's why helium neon laser is widely used in laboratories for all interferometric experiment. Okay, so in our EP lab, second lab, this laser will be there. Helium neon laser will be there. So for interference and diffraction experiment, we'll use this. Okay, so this is the helium neon laser. So in laboratory experiments we will use, because it's so energy and intensity will be very less. Okay, now helium neon lasers are used in supermarket checkout counters to read the barcodes. So to read the barcodes here, we'll use the helium neon lasers. Helium neon lasers. And next one, helium neon lasers. Laser scanners are used for optical character recognition. Okay, optical character recognition. So do you know that optical OCR, OCR scanner? Okay, did you heard this word? OCR scanner. Scanner means, suppose while scanning. So while scanning, so sometimes what happen? So that words are not detected. So if you use normal scanner, so that words are not detected. Suppose so we are taking one hard copy, so we want to scan it, we want to make that as a soft copy, we want to make that as a soft copy. If you scan it, that will come like a image, that will come like a, if you use normal scanner, it will come like a image. But if you use OCR scanner, so it will be, so it will come like a word file, it will come like a word file, that means editable file. So we can change that characters also, that words also. So that means so optical character recognition. So in that scanner, OCR scanner, in that OCR scanner, we'll use the helium neon lasers. Okay. Next one, the helium neon lasers are used by newspapers for reproducing the transmitted photographs. So for transmitted photographs, we will use helium neon laser. And next one, helium neon laser is widely used in metrology, in surveying and as an alignment tool. So metrology department, in metrology department, so to surveying the objects we will use the helium neon lasers. Okay. Next one, it is used in guns for targeting. Okay, it is also used in so for targeting in guns. Okay. Next one, they are used in 3D recording objects called holography. So in holography also will use the helium neon lasers. These are the some applications of helium neon lasers. Okay. Now some disadvantages are also there. There are some disadvantages also there. So those disadvantages are, it is a relatively low power device, which means that its output power is low. Okay, already I said that. So this helium neon lasers are so low power output. It produces the low power output. And next one, helium neon laser is low gain system or device. So its gain also, that means gaining means if you gain is very high means intensity also very high. So this is low gain system, low gain system. So next one, to obtain the single wavelength laser light. So here I said that there are three lasers will be emitted. There are three lasers will be emitted. So one laser will have highest intensity, remaining have very less intensity. So but if you want only one laser, if you want only one wavelength laser means we have to use so we have to suppress the remaining wavelength. We have to suppress the remaining wavelength. So that's why we have to use different another techniques to remove the remaining lasers. So that's also needed some cost. So requires some amount. So some extra so technical skills or extra cost is required. Okay. So that is the one disadvantage. Next, high voltage requirement can be considered its disadvantage. So for discharging, so for gaining the as here we have to supply the so high voltages, that is the one disadvantage. And next, escaping of gases from uh, laser plasma tube is also its disadvantage. We are taking here quartz tube. So So when we apply the high voltage, what happen? It will become the plasma state. It will to the plasma state. So it's more chance escaping the gases. The gases is the another disadvantage is helium neon laser. Helium neon laser. Now coming to the semiconductor laser. So I will explain you briefly regarding about the semiconductor laser. So before going to the semiconducting laser, so do you have any doubts on so this helium neon laser? So because this is a very important one, ruby laser, neon laser, and semiconductor laser also very important ones. That's why I'm so if you have any doubts, I will clarify. Is there any doubts on helium neon laser? Yeah. So now we are okay. So already we know that regarding about the semiconductors. So generally in solar cells you read how to prepare solar cells and how to prepare LED. So LED construction, solar cell construction. Okay, in third unit. Okay, now put the semiconductor laser. So here also by using p junction diode only, so we'll prepare the semiconductor lasers. The laser. So I said that when it takes place. So it should be an optic. There are two types of band gaps will be there: direct band gap and indirect band gap semiconductors. Direct band gap and direct band gap semiconductors. Okay, so which type of semiconductors we have to use here? So type of semiconductor, direct band gap semiconductor we have to use. So direct band gap semiconductor. The examples, there are two types based on their band gap, based on their emission process. There are two types of semiconductors. So one is the direct band gap, another one is the indirect band gap semiconductor. So in case of lasing action, so in case of lasing action, we have to use a direct band gap semiconductor. So if you use direct band gap semiconductor only, so in case of emission process, light will be emitted. If you will use so indirect band gap semiconductor, so light does not emit. So that's why, so we have to use always direct band gap semiconductor while preparing the semiconductor laser. Okay, so now, so how to prepare direct band gap semiconductor? So what are the examples of direct band gap semiconductors? So here, so compound semiconducting materials are the examples of direct band gap semiconductors. How to prepare compound semiconductors? So compound semiconductors are prepared so by group of, so combination of third group and fifth group elements, and so fourth group and sixth group elements. So while using so fourth group and sixth group elements also we can prepare the compound semiconductors. So first one is the third group and fifth group, as well as fourth group and sixth group. By using fourth group and sixth group also we can prepare the compound semiconducting materials. Most of the compound semiconductors belongs to this group. So most of the semiconductors belongs to these third and fifth and fourth and sixth group elements. Okay, now coming to the lasers are made using direct band gap semiconductors. So gallium arsenide is the one of the best example for semiconductor diode laser. Okay, so direct band gap semiconductor is the one in which the conduction band electron can recombine directly with the hole in the valency band. The recombination process leads to the emission of light. I said that. So I said that in last class only. So here direct band gap semiconductor, how we can set that those are the direct band gap semiconductor. So in valency band and conduction band will be there. So if you will take, so this is the 1 minute. Yeah. So this is the conduction band I am taking here. So this is the conduction band. Okay, conduction band this is. Now coming to this is the valency band. So this is the valency band here. So valency band here. So now this is the conduction band. So what are the present in conduction band? So electrons will be present in a conduction band. So those energy levels will be constant. Those energy levels will be either it will vary like this. So it's vary like this. So because the electrons will move always, it will not stable. So it will move randomly inside the conduction band. It will move randomly because the electron is free. So while electron will be there in conduction band, so that electron will be free. That electron will move randomly. Okay, now this is the lowest energy level of the electron. So see here, so these are the lowest energy levels of the electrons. Okay, now so similarly, so holes will present in conduction band. Holes will present in valency band. So this is the highest energy level of the hole. So if valency level of the electron, so lowest energy level of the electron will coincide with the highest energy level of the hole. Okay, so at that situation what happen? So transition will occur. So in that transition direct band gap will occur. So in this transition, so light will be emitted without any loss of energy. So here lowest energy level of the electron in a conduction band coincide with the highest energy of the hole in valency band. So if both are coincide, so at that situation, so photon will be, so that condition is direct band gap condition. Direct band gap condition. In this situation, so photon will be emitted without loss of energy. Without loss of energy. So this is a direct band gap semiconductor. Okay. Now coming to the principle. Okay. So principle. So this principle we will discuss tomorrow. So principle and types of this semiconducting laser. So there are two types are there: heterojunction semiconductor laser and homojunction semiconductor lasers are there. We will discuss those all, and working of those semiconductors also we will discuss tomorrow. Okay. So next, then after CO2 laser. Okay. So we'll complete today. If you have any doubts on this, you can ask. So I will take the attendance. Yeah. So one more thing I have to explain you here. So that is everyone have to submit the third unit assignment. So all questions you have to submit. Okay. So that's all. You can leave now.